Hello everyone, my name is Prohim Tem, currently a master candidate from Department of Software Conversion in Sontanyang University. Today I would like to present about an adaptive support vector machine-based SDN controller toward intelligent network slicing for improving IoT network performance. So today we will go through this content. Let's get started with a brief introduction of IoT application in 5G network scenario. As we may know that currently the exceeding benefit of IoT device in industrial sector, city service, home appliance, and multi-business factor has led to plenty of IoT device implementation. But due to the 5G cellular network deployment with various communication types and massive application service, the exponential expansion of non-automatic adjusting network traffic flow is increasing and also cause plenty of several challenging problems as well. So let's move to what is the real challenging problem in IoT network. In this figure, we try to illustrate about the IoT sensor or end device to the application interface for user. So what is the possible problem that can be occur? So the first one is the data plan gathering. So as we may know that IoT sensor consists a lot of multiple technology, and therefore in order to gathering those type of data set, it's also a challenging way. And the next one is one of the main challenging problem is the lack of adaptive control. So for massive traffic flow between various end device and destination application, it is really challenging to apply any intelligent slicing infrastructure so that the IoT communication network can be avoid from congested and generated longer delay. So it is no way to diminish the network performance. What is the and the final problem is massive IoT handling. So due to the multi-technology, multi-vendor, and multi-standard system of IoT device, it is really challenging to to handle the massive IoT traffic. So how can we possibly handle those problems? Is that we apply our proposed approach, but on top of that, we also need two main trending technology to support our proposed approach. So the first one is network slicing in IoT network. So in this figure, we try to illustrate about the possibility of applying network slicing architecture on top of the conventional architecture to separate, to classify between the very constrained IoT application and constraint and lesser constraint. Let's move into our proposed approach, and the first step is we call it pre-stack procedure. So in this, we ensure that we apply our environment to an SDN environment by applying multiple cluster head, IoT cluster head to each OVS switch. So in this figure, the blue line is referred to the computing flow, and the black and dot line is referred to the data flow, and the red dot refer to the southbound API or by using OpenFlow protocol, and the black line is referred to the northbound API. So due to the massive IoT device, we have to propose an edge server for computing. And in the first step, we take all the data from the data plan to store in the one storage and we start to do the data processing. So in terms of data processing, we will decode the data, and then we will normalization and cleansing the unnecessary or outlier data, and then we will process the data storage. So how can we collect data? Is based on the SDN remote controller, and we store it properly and clean the unnecessary one. So how to design the feature extraction condition is that we import the application layer requirement to our SDN controller as well. And the next step is mid-stage procedure. So in this step, we apply our support vector machine flow for our nonlinear IoT dataset. It is a nonlinear. Very specifically, it requires a lot of kernel to compute, and we select the best one that has the best result in terms of precision or accuracy. So, for example, let's X prime is denote the N feature of training IoT dataset, and the Y prime is denote the M target prediction. So, we will divide it between the testing dataset and training dataset. So, firstly, we will apply our polynomial kernel with degree D polynomial. So what is the degree D? Is that it appears that the degree parameter control the flexibility of the decision boundary, and when the number of degree is higher, it's meaning that the more flexible decision boundary it is. So the the main formula is equal to the multiplication between the target prediction and the feature of training IT dataset, sum with the constant term, and then power of the degree. And then we can make the prediction on the testing dataset parameter. And if the result is not satisfied, we will proceed to step 2. And in this step, we use another kernel. It's also known as sigmoid kernel. It is a hyperbolic tangent kernel. So in this kernel, we require to appoint initial slope alpha and intercept beta. So how to define alpha is that the slope is equal to 1 over n, which is the number of feature of training IoT dataset. And then we will proceed this equation, and if the precision of the testing dataset is not satisfied, we will proceed to the final one is Gaussian kernel, which adjustable sigma. So Gaussian kernel is very alternatively the same to radial basis function. So the adjustable parameter sigma play a major role in the performance of the kernel and should be carefully turned to a problem at hand. So if we assign sigma is too big, then the exponential will behave like almost linearly, and higher dimensional projection will start to lose its non-linear our non-linear IoT dataset. But if we point our sigma lower than the optimal one, the function will lack of the regularization, and the decision boundary will be higher sensitive to noise in our training dataset. So we have to carefully assign our sigma. And this is the formula of OFD kernel, but alternatively in Gaussian kernel it is equivalently the same. So we can use the second one as well. So after applying this kernel, we will identify the optimal one and select to proceed the prediction evaluation and our to apply in our network simulation. So what move to the final state is the software is the support vector machine-based SDN controller configuration. So in this part, we start to configure our SDN controller based on the SVM output. So let's have A, which is denote the I cluster head of data plan, and K is the number of slicing condition. So the first step, we will assign the flow role for I cluster head based on the application target that we imported in step 1 in the pre-stage procedure. And then we will specify the flow entry based on K slicing QoS requirement in terms of the table ID, because each slicing has different table ID and idle timeout, hard timeout, priority number, and for matching we use the we define the part number between the controller and the switch and the action such as type and part. So after defining this separate slicing condition toward our controller, we will assign the remote controller that posts the flow in free URL, which update each cluster head continuously by using OpenFlow protocol. The final one, each cluster IoT device will has its slicing condition separately based on the priority flow. So after this configuration, we will be able to evaluate our proposed scheme with the conventional scheme. So what is the parameter that we use to identify if our proposed is better or not, is improving or not? So there are 5 main parameters that we use in this topic. The first one is latency. The second one is throughput, packet drop ratio, delay, and final one is jitter. After we be able to evaluate, we will prove that our proposed scheme can be used to improve the flexible data plan info gathering based on the SDN paradigm, and then we can configure our SDN controller to be adaptable and flexible and handle the massive IoT and auto control configuration and make it continuously updating based on the machine learning result. And we can well adjust it and classify slicing for each IoT application requirement. So thank you so much for your paying attention, and for any further question, you can contact us on this contact info. Thank you so much.